Okay, so what we're going to do is we're going to go ahead and we're going to look at this warm-up problem. Approximate the open intervals when the function is increasing, decreasing, or constant. So, and then we're going to check and see if the function is even, odd, or neither. So the first thing we're going to do is we're going to go to our calculator and we're going to graph the function so we can get an idea of what it looks like. So on our graphing calculator, we're going to pull up the y equals, we're going to type in our equation, and then we're going to go ahead and graph. So now we get an idea of what this graph looks like. And then what we can also do is we can kind of figure out, we can see here that our graph is going down, down, decreasing until it hits here, the very minimum, and then it's increasing from here. So to figure out the interval of where this occurs, I need to figure out where that minimum is. So I'm going to go ahead and hit second calculate. We're going to go ahead and calculate our minimum value. So I'm going to go on the left side of the min, the right side of the min, and it tells us what that minimum value actually is. So we're going to go ahead and take a real quick picture here. What that looks like, and then we'll talk about that. Okay, so that's our graph. And we're going to go ahead and write out those intervals. So on this portion of our graph, we're going down, so it's decreasing. So it decreases from our x value. Because this keeps on going, the x value goes on forever in this direction, which is negative infinity. And our graph is decreasing until it hits that minimum point, which our minimum value is negative 1.25. And then, once we hit that minimum, we are now increasing. And so it starts at that minimum value of negative 1.25 and goes on for the rest of the graph, which is into infinity. Okay, our next part is to figure out if the function is even, odd, or neither. So the very first thing we're going to do is we're going to go ahead and we're going to test what happens when I plug in negative x into my function. So I'm going to have 2 times negative x squared plus 5 times negative x minus 1. So our negative x times negative x gives me positive x squared, so this turns into 2x squared. 5 times negative x is negative 5x, and then minus 1. Now to tell if it's even, I compare this to our original equation. And if they are the same, then it is even. And it looks like they're almost the same except for the sign in front of the 5x. So this is not even. So now what we're going to do is we're going to go ahead and test our negative f of x. So pretty much I'm taking our function of x and I'm changing the sign of everything. So negative 2x squared, negative 5x, and positive 1. To check and see if it's odd, this and this have to match. And obviously they don't match, so it's not odd, which makes it neither. So there's a little review from chapter 1. And now we're going to go ahead and jump into some chapter 2 content. And we're going to talk about quadratic functions. And so quadratic function is a special type of a polynomial function. And our polynomial functions can be labeled by the degree of the polynomial. And the degree of the polynomial is our term with the highest exponent. And so in this polynomial function, we have a degree of n because my x, that power is to the n, and that's the highest one. And then it just keeps going down as you listed in what we call descending order. So we have different types of polynomial functions we've worked with. We have the constant function where there is no x. So this is the same thing like as a times x to the 0 power. x to the 0 power is really 1, so a times 1, which is a. So our constant function has a degree of 0 because there's no x in there. And then we have our linear function, which has a degree of 1 because that is really x to the first power. And then we have our quadratic function, which has a degree of 2 because that is x squared. And so we're going to talk about how to graph these quadratics, how to write these in specific forms to help us find max and mins and all sorts of stuff like that. Okay, the anatomy of a quadratic. So when we have a quadratic, it's going to look like a parabola, which is that U shape. And so I'm going to go ahead and draw a parabola right here. Now on our parabola, we have certain things that occur. And our first thing that I want to talk about is the vertex. The vertex is the very bottom or top of our parabola, depending on if it opens up, it's the bottom of our parabola. If it opens down like this one, the vertex would be the very top of our parabola. Now, if our vertex is the bottom, this is also known as our min point, and the min point is always going to be our y value. So here where it opens down, our vertex is our max point. And when I'm looking at the max value, I'm looking at that y value. We also have something called an axis of symmetry. It's the line that goes through the vertex. And it's that line of symmetry, so that means I could fold on that line and both sides of that parabola match. And so here, this would be my axis of symmetry. We also have what we call zeros, roots, or x-intercepts. And that's just where it crosses the x-axis. Conveniently, neither one of mine crossed the x-axis, so neither one of them have a zero or a root or an x-intercept. And those words all really mean the same thing, and you'll see them used interchangeably depending on what's going on, which textbook you're using, and how fancy they're feeling. So if this was my parabola, my root would be -8 and -6. We also have a y-intercept, and that's illustrated in this parabola. This has a y-intercept of -6, or in coordinate form 0, -6. And those are kind of our basics of the parabola. Now, with our parabola, we have what we usually call vertex form of a parabola, because in our vertex form, it easily gives us our vertex. So here, h and k are my vertex. Please notice that that's a -h. So when we're looking at that vertex number, we're actually changing the sign, because that minus is actually the opposite of the h value. And then we also have this idea of a pattern of change, kind of like slope, but like slope of a line is constant, it never changes. Here, because we have this curve that occurs, we actually have a pattern of change, and our pattern goes 1a, 3a, 5a, 7a, 9a, so on and so forth. Usually we use 1, 3, and 5, and then we run out of room. And our a number comes from what's in front. If there's no number in front, it's 1. So a sample problem that you'll see in your assignment, we have a function and we want to describe the graph. So the first thing I would talk about is we have a vertex that is -3, because I'm changing that sign, and -5. And then we have a pattern of change, and that's going to tell me how I get the rest of my points. of 1a, 3a, 5a. And our a value is right here. So it's really 1 times that a, 3 times that a, 5 times that a. Which means that for my pattern of change, I'm going to go, because this is negative 2, I'm going to go down 2, right 1. And then because this is negative 6, I'm then going to go down 6, right 1. And then because this is negative 10, I would then go down 10, right 1. I'm going down because it's negative. If it was positive, I'd go up. And actually, it's not just right because of the symmetry, it's actually over. Because I'm going to go right 1 and left 1 in both directions. So we'll kind of see how this occurs looking at some sample problems. Okay, so we're going to practice graphing our function at x equals 1/3 x squared. So the first thing we need to look at is what's our vertex. So this is really saying the same thing as I have 1/3 times x minus 0, because there's nothing inside that squared. And then because there's nothing added at the end, we have 0. So our vertex here is 0, 0. And then my a value is 1/3. So when I'm looking at that pattern of change, I'm doing 1 times 1/3. 3 times 1/3. And then 5 times 1/3. Which means I'm going to go up 1/3 over 1. Up 1 over 1. And then up 5/3 over 1. So here I'm going to go up 1/3 over 1. Both directions. And then from that point, I'm going to go up 1 over 1. And then I'm going to go up 5/3. So that's 1 and 2/3. So here's 2/3 and 1 over 1. Up 2, 1, there we go. And so this is going to give me the idea of what my parabola looks like. Now on your assignment tonight, you're going to be graphing these, but you're also going to be looking at how is that different from my original parent function of f at x equals x squared. So when I graph this, I'm also starting at 0, 0, but I'm going up 1 over 1. And then from there, I'm going up 3 over 1. And then up 5 over 1. And so when I compare those, the purple graph has what relationship to the original graph? And it's actually wider or fatter than x squared. So we're going to go ahead and look at our function at x equals 2x squared. So again, we're going to have a vertex of 0, 0, because there's nothing inside here. There's nothing added on at the end. And then our pattern now is going to be 1a. So if our a is 2, it's going to be 1 times 2, 3 times 2, 5 times 2. Which means from here I'm going to go up 2 over 1. And then up 6 over 1. And then I run out of room. So there's my parabola. There's my quadratic. And then we can compare that to the original graph. So the original graph starts at 0, 0, goes up 1 over 1, up 3 over 1, up 5 over 1, so when I look here, that green graph is actually skinnier or thinner than x squared. Okay, so we're going to look at another graph. We now have our function h is negative x squared plus 1. So now we're going to have a vertex of, there's nothing inside here, so 0, and then I have the plus 1 at the end. So my vertex is 0, 1. And then my pattern of changes here, my a is negative 1. So the pattern is going to be 1 times negative 1, 3 times negative 1, 5 times negative 1. And so now I can graph. So I'm going to go down 1 over 1, down 3 over 1, and down 5 over 1. And there's our parabola. Okay, let's look at the next one. Our vertex. Now we have a number inside, but remember that's a minus h, so I'm really changing the sign. So that's a negative 2, and then this is our y value of our vertex, negative 3. So we'll graph negative 2, negative 3. And then our a value is 1, so it's going to be 1 times 1, 3 times 1, 5 times 1, and that'll allow us to graph. So up 1 over 1, up 3 over 1, up 5 over 1. And there's our quadratic. Okay, so now what happens if I get something that's not in vertex form and I need to write it in vertex form? So we're going to use that idea of completing the square. So what I'm going to do is I'm going to take my x terms and I'm going to put them in parentheses. So that way I can do the completing the square inside parentheses. So to complete the square, I need a number over here that I'm going to add into there so it'll give me that nice perfect square trinomial. I have this plus 5 over here, but because I'm adding this blank space right here, to keep my equation balanced, I have to subtract that blank space over here. So now the question is what number goes in the blank space? So if you don't remember how to do that completing the square, we did it earlier in the year, but no time like the present to remind you. We take our middle term, we divide by 2, always dividing by 2. We then take that answer that we get and square it. So this number should be 9. So if I added 9 here, I'm minusing 9 here, which gives me 0. So it's just like I'm giving up my equation to make over. So now what I'm going to do is I'm going to go ahead and I'm going to factor this. So I'm going to factor that out. So this should now be, y equals, and that should factor into x minus 3 times x minus 3. And that's the purpose. I wanted to get that double root there. And then I combine these, so 5 minus 9 gives me minus 4. Now I can write this in vertex form by combining these to write it as x minus 3 squared. And so now I have it in vertex form. It makes it so much easier to graph. So we're going to try another one, but now we're going to make it more complicated because now we're going to have an extra number in front of that x squared. So here are our x's, but the x squared has a 2 in front of it. So I'm going to pull that 2 out. So I'm factoring out the 2, and so I get x squared plus, and when I divide this by 2, I'm now going to get 4x. So now I'm going to do that completing the square part where I have a blank. I'm going to move this equation out of the way for a little bit because I need some more space. And I'm going to have that plus 7. Now if I'm adding this blank right here, I should be subtracting that blank over here. The problem is this blank isn't all by itself. It's inside of a parentheses that's being timesed by 2. So when I write this over here, I'm going to have the 2 times the blank to make sure that I have the correct number there. So from here, I'm now going to go ahead and take my middle term, divide by 2, and square that value. And that's the number that goes inside here. So now I'm ready to go ahead and factor this. So now I have my function at x equals 2, and now I'm going to factor this x squared plus 4x plus 4. And that should factor into x plus 2 times x plus 2. And then over here, I've got to simplify this. So this really becomes plus 7 and then minus 8. And a positive 7 and minus 8 combine to become negative 1. So now my function at x is 2, and I combine these into 1, so x plus 2 squared minus 1. And you can actually check this on your calculator. Graph this function and graph this original function, and they should look exactly the same. And that's what's kind of cool when you have the colored graphing calculators, because you'll see your first one graphed in blue, your second one graphed in red, and you see how they become the exact same graph. Okay, so our next step is we're now going to talk about how to write the equation when you have the vertex and then just one point on the graph. So we're going to start with our vertex and then our vertex form. So my equation is y equals a times x minus the x value of my vertex. So the x value of my vertex is 1 squared plus the y value of my vertex, which is 2. So I plug that in there. Now the only thing I have to finish or figure out to be able to write my final equation is I got to figure out what this a value is. And how I find a is I'm going to plug in this point that's on my parabola. And that point has coordinates of x, y. So I'm going to plug in x and y. So where I have a y, I'm going to plug in negative 6. Where I have an x, I'm going to plug in 3. Now from here, I'm going to go ahead and solve this equation. So I'm going to simplify this. 3 minus 1 gives me 2. And then I'm going to simplify this more. 2 squared, so 2 times 2 is 4. So this is really a times 4, but I'm going to flip it around to 4a. And now I just have a simple equation to solve. So I'm going to subtract 2 on both sides. So now I have negative 8 equals 4a. Divide by 4. And a is negative 2. And so now I have this last piece I need to write my final equation. So now I'll write my equation. Y equals, my a is negative 2, and then everything else is the same. X minus 1 squared plus 2. And that's the equation of our quadratic. So we're going to try another one. If at any point you need to stop the video, please feel free to stop the video. If you need to, I'm also posting this on YouTube and then linking it to our Edmodo account. So that way you can watch it again if you need to see it again and pause it and rewatch it. Okay, so we're going to write the equation of the quadratic in vertex form if our vertex is 4, negative 1. So I'm going to go ahead and write y equals a times x minus 4 squared, and then plus our y value, which is the same thing, plus negative 1 or minus 1. So now we're going to plug in our point, x and y. So 3 goes in the y spot. I leave a. In the x spot, I'm going to put 2. So now I'm going to simplify like I did before. 2 minus 4 is really negative 2. Now I need to square this. So negative 2 times negative 2 is positive 4. So this becomes positive 4a. Now I'm just solving a simple equation. Add 1 to both sides. So 4 equals 4a. Divide by 4. and our a is really 1. So now I can go back to that original equation. Y equals 1 times x minus 4 squared minus 1. You do not have to write this 1. You could write it as y equals x minus 4 squared minus 1. Either one are technically correct, so it doesn't matter. Okay, so now we're going to go into a new type of problem where we're trying to find the maximum of y equals negative 4x squared plus 8x minus 10. Now, our first hint is to find the vertex. And why would I know the maximum is the vertex? Because since this is a negative 4 right here, I know that my parabola is going to open down. So if I'm trying to find the maximum point, my vertex should be that very max top. So I'm going to go ahead and write this in vertex form, which means I need to take this and I need to factor out that negative 4. So I have the negative 4, and then I'm going to have x squared, and then 8 divided by negative 4 gives me negative 2. I'm going to put in my blank. I'm going to have the minus 10 at the end. But then I'm also going to subtract this blank. But I'm not just subtracting the blank, I'm subtracting negative 4 times that blank, because that negative 4 is on the outside and truly gets distributed. So I'm subtracting negative 4 times blank. Now luckily these negatives are going to cancel each other out, so it's like I'm adding 4 times blank, but we get the idea. So now I'm going to take this middle number and I'm going to do the completing the square. So negative 2 divided by 2 gives me negative 1. I square it to get 1, and that's the number that goes in here. So now I have y equals negative 4, and I'm going to go ahead and factor this portion right here. So that should be an x minus 1 times x minus 1. And then over here I have a negative 10 plus 4 times 1, which is 4. So negative 10 plus 4 gives me minus 6. So now I have y equals negative 4 x minus 1 squared minus 6. And now they're asking me find the maximum. So my vertex occurs at positive 1, negative 6. So I'm saying this one has a coordinate of positive 1, negative 6. Which means my maximum occurs at negative 6. So my max value is actually the y value at negative 6. But it occurs when x is equal to 1. And so when we work with contextual problems, we're going to see how that happens. Okay. So now we're going to look at a contextual problem of where we're going to do this type of thing. So a baseball is hit 3 feet above the ground at a velocity of 100 feet per second and an angle of 45 degrees with respect to level ground. The path of the baseball is given by this function. This is going to get ugly, folks. Where our function at x is the height of the baseball in feet, and x is the distance away from home plate in feet. What is the maximum height? So I'm going to be looking for the vertex of this function. So I'm going to go ahead and take my function. I'm going to factor out this front number. Now to factor that out, I have to take this number and divide by that in front. So on my calculator, I'm going to do 1 divided by negative 0.0032. And that tells me this value is negative 312.5x. Then I'm going to have my space for my completing the square. I'm going to have the plus 3. And then I'm also subtracting that blank. So that's minus the negative 0.0032 times my blank. So now I have to figure out what goes in the blank. So I take the middle term, negative 312.5. I divide by 2 to get negative 156.25. And then I'm going to square that, which gives me 24414.0625. And that's the number that goes here and here. And now I'm going to go ahead and I'm going to work on factoring. So this is negative 0.0032. And then when we were talking about completing the square, I told you about a little trick about if I'm going to factor this, there's a way to know how it factors. It's going to be x and then whatever this one is, whatever I got after I divided by 2. So minus 156.25 squared. And then I still have to figure out this lovely disaster over here. So I'm going to take this number and times by that, 0.0032, and I get 78.125, and then I'm going to add that 3 to it, which means I get plus 81.125. Not so bad when you have the calculator there to help you out. And so now we get the idea of what our vertex is. Our vertex is going to be 156.25, comma, 81.125. If we want to find the max, we want to find the y value. So our max height is 81.125 feet. That's the highest the ball is going to go. Okay. And so we do have another problem, but I don't think we have a lot of time for that. So we're just going to go ahead and skip ahead to our assignment for tonight. 2.1, and I'm sorry I don't have the problems up here, but you have some time, so hopefully you have some time. Grab a book, work on it. Answers will be posted on Edmodo, so you can kind of use that and compare and work on it. The contextual problems, you'll probably have one in your test, but it'll be manageable numbers. Like the example I gave you was actually pretty manageable decimals. Other ones are not as nice. So give it a try, work on it, and we'll keep working on those types of problems all this chapter. And I will see you tomorrow.